And so if what we just saw in our acid was that the substance acted as a proton donor, in other words, it was giving up the hydrogen nucleus. When we talk about a Bronsted-Lowry base, what we're now going to see is we're going to see that the substance in question, the one acting as a base, is in this case going to be accepting a proton. So when we look at a substance like ammonia, what we find is that ammonia, just like the water molecule, had a lone pair of electrons, right? So it has over here, in essence, a lone pair, okay? Now, what does that mean? Well, just like before, it is possible that at a given moment in time, because of probability, the electrons of oxygen all migrate for a split second towards the top of this molecule. And when they do, what's going to happen is that the original electron here of the hydrogen is going to be shimmied and moved away from its nucleus. Well, if that happens, and it just so happens that ammonia is in the vicinity, then what will happen is, as before, the lone pair of the ammonia will now be able to attract the hydrogen nucleus, and in doing so, in taking the hydrogen nucleus, what we're going to find is that it's as if it accepted a proton. And so when we come over to the product side, we see that ammonia produces ammonium, so it's the same ammonia with the extra hydrogen ion, with the extra proton, right? Thus the positive charge. And now we understand how in acting as a proton donor, this is where the hydroxide came out of. Because the hydroxide appeared from the water that in this scenario acted as an acid. It donated his proton and took in process the electron of the ammonia molecule. Now the last thing you want to be aware of is that if a substance that accepts a proton is considered a base and one that donates a proton is considered an acid, then that means that we now have a new way to identify a bunch of chemicals. So for example, in this scenario here, it seemed like the ammonia acted as the proton acceptor. If you recall, my water molecule had the hydrogen here, and then whoop, it moved to there. So in this case, the ammonia was the base, and the water was, and this is important, it acted as an acid. Wait, water can be an acid? And the answer is sure. Did it donate a proton? If the answer is yes, it was an acid. Now, the same way that the reaction could have gone from left to right, we now know, according to equilibrium, that, well, what were to happen if we were to reverse this reaction? In other words, what would happen if we now took it in the opposite direction? Well, if we took it in the opposite direction, then it looks like to me that the ammonium is going to give that hydrogen back to the hydroxide. So over here on the product side, it seems like ammonium is going to be acting as an acid, and the hydroxide is going to act as a base. Now, because they're on the product side and they were created because something had to happen first, so something occurred before we got there, we're going to refer to this as a conjugate acid, and we're going to refer to this as the conjugate base. And all that conjugate means is that it's on the product side, and it's like as if we were doing a conjugation. Conjugation is we did something to it. So we did something on the reactant side that produced these guys over here on the product side. Okay, and so this is how we come up with acid base and then conjugate acid, conjugate base. Likewise, we can do a similar thing when we look at this problem here, and we could sit there and say, hey, it looks like originally I had my hydrogen attached to the hydrochloric acid, right? Now again, HCl, and it was donated. In other words, this guy went bloop, 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 and it was attached to one of these lone pairs there, right? So in doing so, the HCl was obviously the acid, and in this case, the water was the base. Hang on, water can be acidic and basic? And the answer is yep. Now and we'll talk about what type of substance can do both of those. But in doing so, it produced hydronium and Cl-. Now again, if I were to reverse this reaction, if we were to take this thing backwards, then when I do that, it seems to me like the hydronium would have to donate back to the chloride ion the hydrogen. So in this case, the hydronium ion is going to be my acid, and the chloride ion is my base. However, since they're on the product side, you guessed it, this is now a conjugate acid, and this is a conjugate base. Okay? Now, back to our discussion of water. It seems like in this example here, water acted as a base. Yet, in this example down here, we said water was an acid. So which is it? And the answer is, well, it's both. A substance that can act both as an acid and as a base, according to Bronsted-Lowry, is known as amphoteric, or sometimes you'll see it as amphiprotic. Now I like amphiprotic better because to me I understand it, amphibian, so it can switch, and then protic, proton. So amphiprotic, you can accept or release a proton. That kind of makes sense to me. But amphoteric is one that you will often see in textbooks or in papers. So you want to make sure when you see amphoteric, you understand that it could accept a proton or donate a proton. And both of those are perfectly acceptable. So we take it one step at a time, one tick at a talk, and you'll be there in virtually no time.